Okay, kids, one-way slab designs. I've got two examples here. Now, if you are a UCLA student, then you are watching this because you're going to have some questions on the final about it. They won't be numerical questions because you will not have done any homework assignments on one-way slabs, but you're gonna have to be aware of the theory of it. So the questions won't be particularly difficult if you just watch this. If you are a Cal Poly student taking the undergraduate course, then there's not a lot of reason for you to be watching this other than learning about one-way slabs. And I appreciate those of you who are watching this. As of right now, Cal Poly doesn't have a final because we're still not a legitimate class up there. So they never scheduled a final for us. Now, if you're a Cal Poly student, master's student who is taking my advanced course where we're doing one-way slabs and two-way slabs, then you are going to want to listen intently. And you are mainly the people that I am talking to. You are going to have to do your own little project on one-way slabs, and therefore you're going to do everything really that I'm going through numerically. So regardless of who you are, let's get started. Now, the one thing about one-way slabs is you actually have learned everything there is to know already about what you have to do. One-way slabs are an easier version of beams. They are a constant thickness, so the section modulus to the top is the same as the section modulus to the bottom. In one-way slabs, we will take out a 1-foot strip and just design it. I mean, it could be 120 feet wide, but we're only going to look at one 1-foot strip of this, and then that per foot will be how we call out the remainder of the slab, the portions that are identical to the strip that we took out. In addition, we will do a quick shear check just to show you why we never do shear checks. So that messy stuff that we had to do in beams for shear, we don't really do anything for shear in slabs. The idea is that they are continuously supported at all their supports, by beams or by walls. So that continuity of support means there's not a localized high shear demand anywhere. And you'll see that in the calculations. So for this example, 5,000 psi concrete, which is very typical. It's really difficult to ever use less than that because what we want is 3,000 psi at 3 or 4 days. We actually specify it for 3,000 in 3 days. That is so it can be stressed right away. The idea is to pour plus or minus on Thursday and then stress on Monday. So that's the window we're looking for, and we want the concrete to be at least 3,000 psi when we stress it. So we will get 5,000 psi without even trying at 28 days. So normal weight concrete, 40 pounds per square foot of parking loads. By the way, these days, one-way slabs are only supporting parking loads. In fact, beams are only supporting parking loads. They are really just used in parking structures now. Flat plate design, two-way flat plate design really make up all kinds of post-tension concrete buildings. Parking, apartments, condominiums, hotels, office buildings, medical facilities. Those will effectively all be, or are these days, all done in a two-way flat plate slab. So one-way slabs and beams are almost exclusively used in parking these days. Now, I did give you a project, and I changed that stuff up and made some storage and changed the occupancy each year, but that's just for fun and using different loading. But the reality is, if you're doing one-way slabs and beams, you are probably working on a parking structure. As a parking structure, you typically have a 2-hour fire rating. I'll talk in a minute about why that matters. In this particular example, we're going to have 19-foot spacing. So I'm going to jump ahead. My dad did this example. He did a great job. It's very thorough. He didn't use the computer at all, so this is 100% done. Well, okay, 98.7% done by hand. The moment distributions were all done by computers, but this is meant to be your hand example. But this is the design. 5 bays at 19 feet, a 16-foot wide, 16-inch wide beam, 5-inch slab, anchored at mid-depth of the slab, which we always will do. So this is what we're designing. We're designing the slab now. You just finished designing the beam in the project, a 2-span beam. Now we're going to go do the slab that's spanning between those beams. Okay, the Post-Tensioning Institute says slabs should have a span to depth ratio of about 48. When we use that at 19-foot spans, we come up with 4.75 inches of slab. Very typical in parking structures to use a 5-inch slab. That span works in the 17-foot 6 to 20-foot range, and those are the typical ranges that you'll have in a parking structure. So the loading, we have a 5-inch slab. Remember, we do everything in pounds per square foot. Some additional dead load of 3 pounds a square foot. So my dad here is factoring these loads to get some factored loads. So we have factored distributed load of 142.6 pounds a square foot and unfactored total dead and live load of 105.5 pounds a square foot. Now, the minimum tendon cover comes from the actual fire ratings. So that's why it mattered that this was a 2-hour fire rating. To satisfy the IBC, California Building Code adopts the IBC. We are required to have a 1-inch cover at all high and low points for what are called restrained slabs, which the code is defined as every bay in the inside of a structure, so not the end bays. The end bays are considered to be unrestrained bays for fire, and those bays require a 1.5-inch cover. So we have a 1-inch cover on the inside bays, 1.5-inch cover at the exterior bays. That's the way life is right now. Okay, remember my dad's doing this all by hand. He's estimating. Let's start with find a tendon force and profile that we think is going to work. And then design is basically just checking your educated guess. So if you're balancing 60% of the 62.5, that's 37.5 pounds a square foot that we're looking for. On the interior spans, A is 2.5 inches. Remember, I'm going to go to this. This is what we're calculating. The maximum drape or sag we can get on the interior bays is 2.5 inches. Remember, we're talking about small spaces here. We've got a 5-inch slab. We've got at least a 1-inch cover on top and bottom anywhere in that slab. So we're really down to 3 inches of activity. So all this stuff is happening. You know, these slabs are going 19 feet with very little drape. You know, it's actually, when you see the pictures and you see it in real life, it's almost hard to tell that drape is there. You got to look closely. So with the same equation we used before, 8FA over L squared, we rearranged that to calculate the force that we're going to want in the interior bays. Dad comes up with 8.12, so we'll use 9 kips per foot. 9 kips per foot is extremely popular, is very typical, because it actually results in 150 psi average compression. And many firms, our firm, Engelkirk's, when I used to work there, had that as a minimum average compression for one-way slabs anyway. So In a 5-inch slab, everybody was using 9 kips a foot in the typical interior bays. And when you use that, that's 42 pounds a square foot of balance load. In the exterior spans, we actually have less drape. That is because, remember this picture, we can't be as efficient with the drape. We have to anchor at the midpoint, and we also, to the center of gravity of the exterior bay, have 1.75 inches. Remember, we needed a 1.5 inch cover to the tendons. The tendon's a 1/2 inch. So to the center of that is another 0.25 inches. So 1.5 plus 0.25 is 1.75. So we're less efficient here. We don't have the same drape as we do on the inside. So what you're seeing here, I don't want to ruin the movie for you, but we're going to have to add some tendons at the exterior bays. So the exterior span has the 1.375 maximum drape. Therefore, using the same equations that we used up here, Dad's estimating that we're going to need 14.77 kips a foot. Let's round it to 15 kips a foot. So 9 kips a foot on the interior, add 6 kips a foot on the exterior bay for 15 kips a foot. With that 15 kips a foot, the balance load in the exterior bay is 38 pounds per square foot. And the average compression at 15 kips on a 5-inch slab is 250. That's getting up there. We, rough rules of thumb, that's about the maximum you want in a one-way slab. You really don't want to go over 300 psi average compression in a one-way slab. You do what you have to do, but if you're needing to be that highly compressed, you probably should have thought about thickening your slab instead. So okay, here's where we're starting. This is the best guess. This is the good guess. Dad came up with 15 kips a foot at the perimeters, at the exterior bays, 9 kips a foot on the interior. So let's see how well that guess worked. So remember, the first thing we're going to do, you just did your project, you're going to calculate using the actual service loads. You're going to calculate the net moment, the dead plus live minus the balance load, and come up with an equivalent load moment for that. And that's how we're going to check stresses. Stresses, again, are checked on service dead load plus live load minus the post-tensioning loads. So we're also going to have to do something. I'm going to jump ahead so that you understand. We're going to have to pattern loading, which means that we're going to use the computer program. PT Data is going to do this for us, but we have to come up with the pattern of loading by patterning the live load. You really can't do anything about the dead load. It's always existing in all the spans. But to get the worst negative moment, so the worst moment, tension on top at B and E, we need to pattern the live load such that that happens. So we actually want maximum live load on each side of B. Then we take it off, then we put it on, then we take it off. And so that will give us the maximum negative moment at B, which, since this is symmetric, we will use at E also. But this pattern loading is actually created such that it's absolutely the worst at B. Not really at E, but then because it's symmetric, we're going to use what we get at B at E. So maximum negative moments at C and D. This is set up to give me the maximum negative moment at C. I'm going to have maximum live load on each side of grid C. Then I'm going to take the live load off at the next base. Then I'm going to put it on at the next bay after that. If you ever study pattern loading, to get the most negative moment, you have to put the live loads immediately adjacent to the joint that you're looking at. And then it's a series of taking it off, putting it on, taking it off, putting it on. Each one of those bays, by putting on the maximum live load here, you're actually creating, through continuity, a worse condition over here. So that's maximizing this. I said you're probably going to have to study that on your own a little bit, but you can take my word for it. Then, of course, we're looking for maximum positive moments in the various spans, and we're doing the same thing. We're putting the live load on those spans and taking it off the adjacent spans and then putting it on the second span over. That actually creates the worst condition for the bay in question. So, that's what Dad is doing here. Full live load means that we have the full interior span. Total load minus the pre-stressing load would be 64 pounds a square foot. That's with full live load. In the bays where we're going to take the live load off, our total load is just the dead load now. So now we're just the dead load minus the pre-stressing load. And in those bays, we have 24 pounds per square foot. The exterior spans, when we have full dead and live load, this is full dead and live load minus the pre-stressing load. In the exterior bays, we have 68 pounds a square foot. Then when we take off the live load, this is now just the dead load minus the pre-stressing. We'll have 28 pounds a square foot. So these combinations will be used for the pattern loading to get us the worst case, the worst negative moment, the worst positive moment that we can come up with at various locations. And these are the patterns that will be used. PT data does this. Dad doesn't show that. For those of you at Cal Poly in my advanced graduate course, you are going to use PT data. You're going to tell it. You'll see this in the second example. You're going to tell it to skip the live loads. Skipping loads is another word for patterning the live loads. So the result of that in this case, the worst negative moment we're going to get based upon any of these combinations is negative 2.49 kips per foot. Remember, everything is in per foot. So foot kips per foot. Interior bays, the worst that we're coming up with is 2.2 foot kips per foot. And then these, since the system was symmetric, are the same. For the positive moments, with these, this is the load pattern that created that moment. That moment is also used over here. Again, symmetry 1.24 foot kips per foot in the first interior bay, and in the middle bay 1.73 foot kips per foot. Okay, so you'll remember from what we've done in your project, stresses are always minus F over A, and then it's plus or minus M over S, depending on if we're looking for worse compression or maximum tension. Section modulus is pretty easy, in a rectangular section. Remember, our section, head back here. This is the entire analysis. All of our calculations are based upon this section. So, section modulus for a 5-inch slab, BH squared over 6, is 50 inches cubed. Doesn't matter if it's to the top or to the bottom. It's symmetric. It's the same. Remember, just like in beam design, allowable flexural tension stress is 7.5 square root F prime C, or 530 psi. Allowable compressive stress is 0.6 F prime C, and that'll be 3 KSI. Just like in beams, just like in anything, if that is limiting your design, you're in trouble. Compression should never play a part in this, but it is a code requirement, and we are going to check it. So we're checking the stresses now. We're going through the same steps and the same process that you went through in your project. So stress design minus F over A plus or minus M net, which is 200 or 2.01 foot kips per foot, negative 0.15 plus or minus 0.42. So we get 332 psi at the top and negative 632 ksi at the bottom. So tension at the top where we'd expect, which is what we would expect, and the bottom of the joint is 632 psi. Not something we would normally check, but in the academic world we're going to. So you can already tell that that's less than 530. We're looking pretty good. That supports B and E. We have 2.45 kips a foot. Remember, at those locations, we actually have 15 kips a foot. So our negative F over A is 15 kips over the 60 inches squared. That's that 250 psi negative. Plus or minus M over S with the 2.45 results in tension 338 psi at the top and negative 838 ksi at the bottom. Again, the one we really care about is this one, and this is less than 530. It's looking good. It's looking very good. Let's look at the exterior spans. Again, the very exterior span has the 15 kips a foot in it. So the F over A portion, the negative 15 over 60 is the negative 250 ksi. M over S with the positive moment, plus or minus 559. Therefore, we're looking for tension on the bottom in the exterior spans, and we get it. 309 psi tensile stress on the bottom, negative 809 psi on the top in compression. So again, this is less than our allowable. I'm feeling good about this. So sorry about that pause, but for some reason Camtasia, if I go more than a half an hour, just stops itself. So I keep having to do that at about 25 minutes on my own. So let's look at the interior span. This is not going to be any surprise. We're at 173. We only have 9 kips a foot for F over A in the interior span. So minus 150 plus or minus 415 means that we have 265 psi tension at the bottom. Once again, less than 0.530. So the other spans are even in better shape with the 9 kips a foot. All flexural stresses are met. Therefore, just like with the beam project that you did, once the service stresses are checked and work, that sets the post-tensioning. So we're going to use 15 kips in the end bay. We're going to use 9 kips in the interior bays, and we're going to drape them like this. Post-tensioning is now set since the service stresses have been shown to work with this force and profile. We can't change that for anything that we're going to do in the future. And in the future is now, we are going to calculate the strength. So again, sound like a broken record, but just like you did in the beams, We're going to factor the dead load and factor the live load. That is, by definition, MU. And we need to add 1.0 times the secondary moment. So just like you did in the beam design, at this point we need to calculate what the secondary moments actually are. You will recall that the secondary moment is the pre-stressing moments, balance load, pre-stressing, that's not pretty, minus the primary moment, primary pre-stress moment, F times E. So let's look at what the primary pre-stress moment is. Remember, we have to go back and look at this. The primary pre-stress moment is the force times the eccentricity between the center of gravity of the concrete and the center of gravity of the tendon. So we're looking at this distance between those 2 points. This is set at 2.5 inches down. The center of gravity at the top of this is at 1.25 inches. So therefore, our eccentricity between the center of gravity of the steel and the center of gravity of the concrete is 1.25 inches. That, by the way, is the same at all these locations. So at B and at E we have 15 kips for F. So F times E, that's E, is 1.56 kips, foot kips per foot. At the interior bays we have 9 kips times E, 0.94 foot kips per foot. So now we're just putting on the equivalent loads. Remember, you did this. One of your load cases in your beam project was to put on the equivalent loads only and calculate those moments. When that is done, and remember, all secondary effects just happen at the supports. They're due to the support restraint. So you really don't have to study anything other than the results that you get at the supports. So the equivalent moment, 1.73 or 1.28. The primary pre-stress moment, F times E, was 1.56 or 0.94. Secondary moments are going to be the difference between those two. So if you don't believe me, take out your calculator. You can do this by hand. 1.28 minus 0.94 is the 0.34. So if you will recall, any normal layout of force and profile creates a secondary moment diagram that has the tension on the bottom. And that's what we have just proven here. The secondary moment diagram is entirely a tension on the bottom moment diagram. These are the secondary effects, the secondary moments, which must be included in the strength design. So notice again, they will subtract from the negative moments, kind of helping us at the negative moments, but they add at the positive moments, just like they did in your project and the homework assignment that I gave you. So let's move on to the factored total load, dead plus live, and the factored dead load. Again, we have to do the same thing we did before. For strength, we need to come up with the maximum worst case patterned negative moment at each location and positive moment at each location. So I think you understand the theory and the process. pain in the butt to do it by hand. None of you have to, even those of you taking my advanced course. You're using PT data now. I'm just telling you what it's doing. You are using the program, you're using AutoCAD drawings, and you're going to draw and create the design for one floor of a one-way slab system. So this is what PT data is doing for you. It's looking at all of that, and it's coming up with maximum demand moments. Remember, these we had to come up with our own term for. Demand moment. So what's happening here is the result of just the factor dead and live load was 5.75 negative foot kips per foot. Remember, the secondary moment actually helps that, actually reduces that negative moment. So instead of designing for 5.75, we're actually designing for 5.58. But in the positive moment range, we calculate factor dead plus live load as being 4.51. We must add the portion of the secondary moment, which is 0.17. It was 0.17 right here. So divided by 2 for the midspan. We're going to have to design for 4.6 foot kips per foot at the end base. And likewise, the same philosophy is happening here. But it's important to remember, in one-way slabs, two-way slabs, beams, that secondary moment is there. It's statically correct, and it's required by code to be included. So, like I said, anything that's not unusual, it will be reducing your negative moments. It will be increasing your positive moments. Just like we did with beams, we need to start with a amount of bonded reinforcement. Now, it makes sense that the amount that we'd start with to check would be what's minimum required for bonded steel. That same, and this is a good question to ask on the final, the same exact requirement for beams are required in one-way slabs. They are not the same minimums in two-way slabs. You're going to see two-way slabs either from Brian or from me in the next lecture. But in one-way slabs and beams, they're both considered one-way systems. They're just spanning in one direction, not spanning, not taking load in the perpendicular direction. For one-way systems, the minimum bonded reinforcement is 0.004 times the area in tension. So remember, the area in tension it's a 12-inch wide slab. It's 5 inches deep. If you're looking at the top or you're looking at the bottom, you're still looking at the same area. It's half of the depth. So when you have negative moment on top, this is what we're talking about. When you have negative moment on the bottom, this is what we're talking about, but it's the same number. It's going to be 12 inches wide times 2.5 inches deep, or 30 square inches. Multiply that by 0.004 and get 0.12 square inches per foot. So in a 5-inch slab, I've been doing this a number of years. I just know that that means the minimum steel is number 4 is at 20. So most 5-inch slabs will have 4s at 20 in them. There'll be a few localized areas that might need more than that, depending on span changes and stuff like that. But for the most part, the vast majority of a 5-inch slab has 4s at 20 inches, top and bottom. That's the minimum required on the top, which is also the same minimum required on the bottom when you have tension on the bottom. So let's look at the supports at B and E, where we have the 15 kips a foot. We have a demand moment of negative 5.01 foot kips per foot. That's MU plus 1.0 times the secondary. Everything is the same as it was with the beams, except the FPS equation now has a 300 in it for slabs. Now it gets confusing sometimes in UCal Poly advanced students. If I give you a span that's short enough, you actually might have a span to depth ratio that's 35 or less. And at that case, this switches this to 100. That's one of the very confusing things about the code. And we're trying to actually get that changed. It was never the intent that one-way slabs would change the FPS value from one span to another. That really doesn't make any sense. And if you actually think about it, it's actually changing within inches of the interior support. That doesn't make any sense. So we're trying to get to the point where all one-way slabs will just use the 3000 or the 300 in the denominator. Okay, so APS will just ratio the 15 kips per foot to 26 kips, 26.6 kips per tendon. 0.153 square inches. We're still using half-inch diameter tendons. So our APS per foot, 0.086 square inches per foot. Remember that for 5,000 PSI concrete, hopefully it's locked in your head by now that beta 1 is 0.8. So rho P is that 0.086 area of pre-stress divided by 12 inches divided by dp. So dp is 3.75 inches. So we have a rho value of 0.0019, which sets the slab FPS equation to 192.8 KSI. Remember, what that is saying is that at failure, at that location, you know, when the sky is falling, the whole place is falling apart, you can expect to have 192.8 KSI of tensile stress in the post-tensioning steel. And you can use that to calculate your strength at failure. So TP is the 192.8 KSI. Per foot, we have 0.086 square inches. So per foot, we have 16.6 kips of force in the tendons per foot. The rebar, 0.12 square inches per foot. That's what number 4 is at 20 will actually give you. Times the 60 KSI is the 7.2. Those are acting in the same plane. They'll be side by side in the slab. So they both have a 1-inch cover. They're both half-inch diameter themselves. So they're in exactly the same plane. Static says that this plus this must equal the force in the concrete. So we know the force in the concrete. We don't know where it is. But we have another equation for force in the concrete. 0.85 F prime C B times A. So we'll rewrite that in terms of A so we can know how deep, where that concrete force exists. 0.47 is the Whitney stress block. And the neutral axis depth, just to make sure we're tension controlled, we will check that with 0.59 inches. So here's Dad checking that the strain in the steel is greater than 0.005, which it is. It's tension controlled. Slabs will basically always be tension controlled. And we sum moments and put a 0.9 factor on it. and get 6.26 kips per foot, greater than the demand moment. Okay, we don't need to add any more rebar at those interior joints. Go through the same process at the interior joint. The demand moment was less. We're back to 9 kips a foot for the pre-stressing on the interior spans. We go through the same process, calculate rho, calculate FPS, calculate a force per foot in the tendons, calculate a force per foot in the number 4 is at 20. Add the two up, get the total force in the concrete, calculate the Whitney stress block, calculate the neutral axis depth. You know, these are kind of academic numbers that my dad's doing because this works by a factor of 6, which it will typically. You know, as long as you're not loading up any member with a ton of reinforcement, you should be tension controlled. That's the idea. That's the theory behind being tension controlled. You don't want too much tension reinforcement. Let that concrete work in compression. Let the tension steel yield, and it'll be a controlled type of failure. So we're good. At number 4 is at 20 with 9 kips a foot of PT. Some moments, put a 0.9 on, 4.69 foot kips per foot of capacity is greater than the demand. We're good. Do the same thing at the positive moments, just everything's upside down. I don't even know that I need to go through all this. I think you all can get it. In the first end bay, we have 15 kips per foot with the added tendons. So we have a higher APS. We have a higher rho. We calculate an FPS value of 191.6 there. Determine the 2 tension forces and the compression force in the concrete. Again, we're working by a factor of 3 here for strain in the steel. That's pretty academic and not something you're going to typically need to check anymore. But you Cal Poly students in my advanced class, I still want you to do it. It'll be one of the only times you're actually doing this. Calculate the moment capacity, use the 0.9, come up with a positive capacity of 5.62. The demand, even with the addition of the secondary moment, was 4.6. It still works. So everything is working. It's 19-foot span with a 5-inch slab with 9 kips per foot in the middle, 15 kips per foot at the 2 end bays, and 4 is at 20 throughout, top and bottom. Works fine. Not at all unusual. In fact, these slabs will be the most typical slab, a 5-inch slab going somewhere in the 18 to 20 foot range will be what holds up cars in long span parking structures. It's been that way for 40 years and it's going to keep being that way. So rarely do you have to add anything beyond minimums. You saw that in your project for beams too. And if you're adding something, you're adding one more bar in the beam. I probably had you do that in the project. You may be tightening up. This 4 is at 20, may have to go to 4 is at 16 or something like that on the first interior span. That's about the worst thing that happens. Dad's talking about inelastic redistribution. That's a topic that we're not going to get to, but the code actually allows you to inelastically, through plastic moments, redistribute some of the negative moments to the positive moment sections. That wasn't necessary for us to do. It's never necessary that you do it. It's an option available to you, but that's kind of a more advanced topic. So you're going to have to actually discuss that somewhere else. Now, I told you we're not going to really check shear, but we'll check shear for fun, just to show you why we never check shear. So half of the span is 9.5 feet. This is an approximate check that my dad's doing, multiplied by the maximum factored dead plus live load is 1.36 kips per foot of shear along the beam, along the slab as it's resting on the beam. The capacity, just using the concrete alone, 0.75, 2 square root F prime C. We're looking at a 12-inch section, and D is allowed to be, or not required to be taken less than 0.8 H. So the shear capacity is 5.1 kips per foot, and our worst case demand was 1.36. Again, you're not going to do this. I'm just showing you, or my dad's showing you this so that you understand why you really never have to worry about it. The point is the slab is continuously supported. It's not like two-way slabs that you're going to see, which bring all of their load to a localized point at a column. That can be difficult to resist when you're lumping up all of your shear demand at one localized point. You likely have a shear problem that you have to deal with, something you have to think about and design for. When you're continuously supported, which is what one-way slabs are, very difficult to develop a shear problem. So that was the example that my dad came up with. Just to show you, the computer calculates the deflections. That's just getting beyond anything we need to do, and it's mainly because it never ever controls. You're typically somewhere in the allowable deflection range of L over 360 or L over 180, depending on if you're looking at total loads or live loads only. And I'll be honest with you, so little of anything I ever do is controlled by deflection that I don't even think about those very often. But out of PT data, you will see that the deflections that we have are tiny. These are the dead load plus pre-stress deflections. 0.09 inches, 0.02 inches. These are tiny numbers. The live load deflection just by itself is still tiny numbers. 0.16 inches of deflection. These L over values, L over delta, L over 1432. You're nowhere near the 180 or 360 or whatever you've decided your limiting factor for deflection is. We're in the thousands here. 9,053. So for post-tension concrete, we have effectively solved the deflection issue just by the fact that we lift it back up. So this will be the final design for my dad's example. Now I've done another example. It's actually very similar to that one, but this is more in line for you Cal Poly graduate students. I'm going to integrate, first of all, a pour strip, which almost always comes up on one of these projects. And how that gets handled is confusing to some practicing engineers, so we're going to talk about that. I have a 5-inch slab just like we had. Really not any reason to do an example with something different than what happens about 90% of the time. So I'll stick with 5 inches. 18 feet is the typical bay, and I've got an end bay of 13 feet. That's what we try to do. We try to make the end bays shorter so we don't have to add those tendons that we did in the last example. Sometimes you get that and sometimes you don't. You're left with what the architect is going to give you, parking consultant. But it's not that unusual to get a relatively shallow exterior bay, which helps us because of the fire rating, the fact that we can't get the full drape in the end bay. That was the reason why we had to add the tendons anyway. So I'm going to show you now how to use a little bit more of PT data, which is what you Cal Poly students are doing if you're taking my class on slab design. and we're going to show you how to integrate this pour strip. So I get the same loads that Dad had, 40 pounds a square foot of parking loading, 3 superimposed, which it's hard to figure out how any of that is actually really there. You know, the funny thing about electrical conduit is it's actually a void in the slab. So if anything, the electrical actually decreases the load. It doesn't increase the load. But we put it in there anyway for fun. So this is what we're talking about. We are designing rebar and post-tensioning to drape between the beams. These are the beams. This is what you designed in the project. Now we're designing the slabs that span to each beam and over it. So I go into a dissertation here about why we're using 5,000, but I've already explained that we want 3,000 PSI at transfer, and we're going to get 5,000 whether or not we want it or not. I'm talking about the fire protection here, which is what we already discussed in the previous example. So I'm going to kind of blow through the things that my dad already did in his example. You know, I'm coming up with an estimate also of an average force, 8.17. We're going to end up using 9 kips a foot magically, because we always do. And because I have a short end bay, I'm going to end up using that 9 kips a foot at the end bay too. So I'm balancing about 88% of the slab weight with that 9 kips a foot. And we'll look at the end bays. We're balancing a little bit less. Oh, I lied. Balancing more. Because of that 13-foot bay, I can balance a lot of the load. So probably should look at my example a little closer before I do it. So we're in the range of 80 to 100% of balance load. Doesn't look like we're going to have to add any additional post-tensioning. So we'll let PT data go to work. We build this in the computer program. You students doing this in my advanced class, this is what you're doing. By checking this box, making sure that the live load arrangement is skipped, you're telling the program to do this for your moments. For your moments for stresses, for your moments for strength. You tell it that we want 7.5 square root F prime C. We've got 5,000 PSI concrete. That 1.5 is the end span concrete cover. By the way, I've rearranged this window in the latest version of PT data, so it's not going to look exactly like this when you use it, but it's a little bit cleaner, a little bit more organized. Remember, in span 8 here, we have a pour strip. So the question that comes up, you know, we've just gone through, and I think it was pretty simple how to go through and fully drape all the bays, how to do the stress calculations, how to do the strength calculations. When you have a pour strip, a little bit more involved, a little bit more thinking. So in this particular bay, let me back up. This is what a pour strip looks like. So tendons are coming along here, high over the beams, low, and you're going to anchor at the midpoint at 2.5 inches from the top and bottom into the pour strip. This pour strip is there for a variety of reasons. Probably the most important one is to allow the slab to shrink as 2 much smaller pieces of slab instead of 1 large piece of slab. So we're trying to allow shortening and shrinkage to happen in smaller chunks. Then we're going to connect it all together. So we will stress into the tendons into this bay, but it's anchored at the midpoint. And we'll add a lot of rebar in here because we don't have post-tensioning. So the post-tensioning is going to stop here and it's going to stop here. So this part of the slab needs to be designed entirely to work in rebar. And that's why you're seeing this lapping rebar coming in and more of it in this location. So back to the modeling of it. Whereas you're fully draped in all of these bays to 3.75 inches from the top to the center of gravity of the steel, in the pour strip bay, we're only going down to 2.5 inches because that's as deep as you're going to go. That creates a much lower balance load and potentially some stress issues. But remember, we are designing this bay entirely in rebar, so these stresses technically don't matter. You're allowed to make sections of slab work entirely as a rebar mild reinforced slab, and if you do that, then you don't have to satisfy any of the post-tensioning requirements. It's really your choice. So I've got 9 kips a foot throughout most of that pour strip bay. I've got a big zone, a 3-foot zone, not a big zone, but a 3-foot zone in the middle of it that doesn't have any pre-stressing in it. But I'm anchoring it at the low point. And then all the rest of the slab interior bays will be the full 3.75. So there's something a little deceptive that's happening here. If I come back up here, that 254 is what the stress is that PT data is calculating. But in reality, you don't have any F over A. You don't have any pre-stressing in that middle 3 feet. And that's actually exactly where this is telling you that it's calculated the stress. So it's not really correct. So what we do is we come back in then and model that one pour strip bay with no pre-stressing in it. Now it does have pre-stressing in it all the way until it hits the pour strip, but we're bounding the problem. We're doing one run that has the post-tensioning for the entire bay, even though it's not really in the middle 3 feet. But then we're going to do another analysis that takes out all the post-tensioning in that entire bay, which will bound the situation. So when we have no F over A and we have no balance load, we end up with a much higher pre-stressing tensile stress, which still ironically works. It's still less than the 0.53 required. But we're not really a pre-stressed concrete slab there. So again, all that we really have to do is make this work as a rebar slab in this section. But what we really care about under both situations is that we're not exceeding the stresses where we actually have post-tensioning over the beams adjacent to it. So we're okay there. Now when we go to the rebar requirements of the post-tension slab, in the analysis that has the post-tensioning set to 0, we will see that we need number 4s at 15 inches on center there. So the program actually does the work for us. It knows what the demand moment is. It calculates the rebar required for that bay entirely as a rebar bay. So we will lap that steel. We don't want it crossing. We want both sections of concrete, this side to be able to shrink that way and this side to be able to shrink this way. Theoretically, that pour strip will grow in width a little bit. Once that's done or stops moving appreciably, then we fill it in. So pour strip is providing a stressing location, so if our tendons were getting too long for double-ended pulls, that solves it. And secondly, it's allowing the concrete to shrink in smaller sections. So it's providing two things for us. Okay, so we'll go back in, look at the minimum bonded reinforcement just like we did in the last example. Strangely enough, we get exactly the same answer as we did last time, 0.12 square inches per foot, which is number 4 is at 20, which I told you is always the minimums in a 5-inch post-tension slab. So I'm just going to show this to you. We already went through this earlier in this lecture. FPS, come to this diagram, calculate the force in the concrete, force in the tension steel, bonded, pre-stressing, calculate the moment capacity, put a 0.9 on it, come up with 4.7 kips per foot of capacity. PT data will tell us what our demand moments are, so you, my Cal Poly students or graduate students, don't need to calculate the dead load, the live load, factor it, figure out what 1.0 times the secondary effect is, secondary moment. I may ask you to do that in the project to verify one location or so, just so you can show me and remind yourself where those things are coming from. But PT data does all that work for you. So these are the demand moments. There's a maximum positive and a maximum negative based upon the skipping of the live load. So you've got to figure out which one of these at each location is your larger one. Not hard to do. So you get the point. It will actually calculate the area of top and bottom steel if you need any. This has nothing to do with minimums. This is only for strength. So the numbers here will be compared to the minimums required, and the largest requirement will control. Most of the time, you don't need any, or you need very little for strength bonded rebar. The minimums will control. Now this is something that didn't occur in my dad's example, so I would like to go over it. The code tells you minimum lengths of that bonded reinforcement. So you have the minimum 0.004 times the area in concrete in tension. That establishes the rebar that you need, but this establishes the minimum length of that rebar. So ACI 77441A says that for bonded positive reinforcement, at least ln over 3. So the length of this bottom bar in the span, ln means the clear distance. So ln is 16 feet 6 inches here. So I must have at least 16.5 feet divided by 3 of positive moment, and it says centered in those areas. So you can't put in less reinforcement than this. If for strength you needed more than that, then you'd have to put it in. Most of the time we're really just talking about the minimum steel, so the minimum length requirements are all that have to be there. Now 7.7441B says for negative reinforcement, you need the clear span divided by 6 on each side of the support. So this is the clear span divided by 6 plus the width of the support. So you've got 2 of those plus the width of the support. 2 ln over 6 plus the 18 inches. Says that the top steel that I need to specify can't be any less than 7 feet. And the bottom steel Can't be any less than 5.5 feet. If you draw this, you'll see that you actually have a zone of no bonded reinforcement. That's begging for a crack. That really is just saying, hey, I really would like to crack here. So you have no bonded reinforcement. That's where you can look for a crack. So what we do, there is no structural integrity steel, which we haven't talked about yet, but when we get to the two-way slabs, there is a minimum amount of integrity steel that needs to go through supports, bonded integrity steel or unbonded integrity steel. There's no such concept in one-way slabs. So I mean, you haven't heard of it, so don't let that confuse you. But when you get to two-way slabs, we're going to have some what we call integrity steel. It says regardless of what we need for strength, we're not going to have any zones that don't have some type of reinforcement in them. One-way slabs don't have that. But what engineers will do is we typically run 25% of the steel continuous. There may even be a code requirement that says that now. We've been doing that for so long. I'll be honest with you, I get a little confused about what are our office requirements and what are the code requirements. But common sense says some of the rebar should be continuous. So our drawings, 25% run continuous and lapped. Here's another topic that is kind of the final thing I'm going to go over. It wasn't in the first example from my dad. Perpendicular. You know, our slabs span one way. These are one-way slabs. They're spanning beam to beam. That is the one direction that they're working. What's happening in and out of the plane is irrelevant from a strength perspective. The span, we could be 100 feet, we could be 200 feet. The slab is not working in that direction. That's why it is a one-way slab. But the code says you still need to provide temperature and shrinkage reinforcement for that direction. We don't want the slab cracking up in that direction, even though it's not working or technically flexing in that direction. So this is temperature and shrinkage requirements. Now you can do this with bonded steel, or in post-tensioning you can do this with pre-stressing steel also. It is the most common to actually calculate pre-stressing steel to satisfy the temperature and shrinkage requirements. So what the code says is that you must provide a minimum of 100 psi on the gross area of concrete. So remember, before when we were doing this, we had a B effective (16T) plus the width of the beam. Now we're looking at the full tributary section. So we're going halfway to the next beam. This isn't the T-beam section that we're using. We're actually looking at the entire tributary area and trying to figure out what average pre-compression we have over that full area. Now in this design, you can assume we had 10 tendons in the beam. Okay. The code actually requires that temperature and shrinkage post-tensioning not be spaced any farther than 4.5 feet. If you go more than 6 feet, you have to add bonded reinforcement. Sorry, I'm going to restate that. Under no circumstances can you be greater than 6 feet. Anything greater than 4.5 feet requires added rebar. So, sorry I misstated that. There's no point in going to the 6 feet. We're just going to limit the temperature and shrinkage tendons to 4.5 feet on center. So in this case, that will add 3 tendons within this zone. So the total number of tendons that we will have inside the full tributary is 10 from the beam plus 3 in the slabs times 26.62 kips per tendon divided by the full area of that tributary section. And we easily satisfy the 100 psi. So from that perspective, we have enough pre-compression to satisfy the code. The code just says you need 100 psi and you're okay. We're at 220, but the kicker is we can't space these out any farther than 4.5 feet. So regardless of the fact that we're killing the 100 psi, we've got to have tendons at 4.5 feet on center. So that creates, in 16.5 feet, if I've done the math right, without going any farther than 4.5 feet, that will result in 3 tendons within each bay. And that's actually how we will call it out in on our drawings. We'll say each bay gets 3 tendons at the CGS. So that covers pore strips and temperature and shrinkage steel, which you didn't see in the first example. But it's an integral part of doing any one-way slab design. Again, we can talk about deflections, but it's the same as it was last time. You know, it's L over 42,190. We don't have deflection problems in post-tensioning, which is one of the greatest reasons to use post-tensioning. Here's a picture of some hardworking people, and I don't envy them. You know, my knees, 57 years old right now, just looking at this, I feel pain. But these guys are doing a beautiful swirl finish. It really looks like artwork, and these guys are artists in their own way. That swirl finish actually creates friction for cars as they're driving. So instead of having you don't want a smooth concrete surface as you're driving around. You don't want wet wheels to spin. So these people are putting in a swirl, which not only looks good, actually has a function to it. It actually helps the tires grip, and when you're walking, you know, help your shoe grip to the concrete. Okay, that's it. One-way slabs. Depending on who you are, we'll see how useful that is. You UCLA students, like I said, nothing numeric, but things I like to ask are it's very similar to beam design. One thing you think about is that the 0.004 minimum area of rebar is the same between beams and one-way slabs. That's a very typical question that I like to ask to make sure that you watched this video. Okay, see you later.